Welcome to my study once again. Today we're going to talk about Geary chapters 5 and 6. So chapters 5 and 6 are precursors to the more interesting material that we'll get when we turn to chapters 7, 8, 9, and 10. So those chapters concern how to look for causation and test for causation and the statistical treatment you need for underlying causal studies. And then chapters 9 and 10 will turn to applications of this material to decisions. How do you use the kind of information we've acquired to understand decision making when it goes as good as it can possibly go? In any case, for chapters 5 and 6, we need to look at statistical matters. Some of you will already have taken statistics. This will be just a very rudimentary summary of things that you probably already know. For others of you, this is a very baby introduction, low-level introduction to the kind of thing that you will study at a more serious level if you end up taking statistics. So we're going to do a little bit about probability, proportions, distributions, and we will do a little bit of practical work on applying the probability calculus so that your understanding of probability is in place prior to getting to the work we're going to do on understanding causal hypotheses. So let's turn to the slides. Our task for this part of the course is to understand the Geary method, the Geary program for making sense out of statistical and causal hypotheses. These are the kinds of things that we see in science that rely on population level distributions of features. It turns out this is probably the most interesting and relevant parts for ordinary life because you're seeing statistical reporting and taking it into account nearly on a daily basis. It happens in politics where you're looking at polls and survey patterns there. More interestingly, it happens with data about health and well-being all over the place. How much vitamin D should you get? You're worried about skin cancer, but you're also worried about deficiencies in vitamin D. So how much time in the sun? How does sunscreen affect the reception of vitamin D? Is coffee good for you or bad for you? Is wine, red wine, good for your health, bad for your health? How much chocolate should you be eating? All of these sorts of things get reported on every day. And sometimes it's a blithering array of confusion that results. So we're going to look at some of these sorts of things and what to look for. The chocolate example is probably the best of all. We're going to learn a little bit about something called p-hacking, because the chocolate example is a perfectly good example of how researchers, well, it's not the researchers so much as the advertising people who use certain research without informing you of the details of the research. So chocolate was supposed to cause weight loss, enhance your chances of losing weight, which is a rather astonishing thing to be told. One would think chocolate introduces more calories, add calories to a diet, you don't get weight loss, you get weight gain. In any case, that's what we're going to be aiming at. So let's talk a little bit about the goals. Let's talk about the kinds of models that can be proposed according to Geary. Turns out there's only 3 for these 2 chapters, so that simplifies what we're looking at, and then we're going to start working on statistical hypotheses and what to look for in our understanding of them. So the goals have to do with the relationship between a population and a sample of that population. When we learn about a sample and we know how the sample was constructed, how large it is, we want to be able to calculate an estimate of what the actual population is like, how much confidence to place in that estimation, and how good the evidence is for our claim that the sample fits the real-world population. To achieve these goals, we need to learn about each of the following: proportions, probabilities, distributions of random variables, frequency, and the probabilities of such distributions, standard deviations, margins of error, confidence levels, and the notion of statistical significance. Lots of terminology, but there's really three fundamental things: proportions, probabilities, and distributions that will form the core things that we need to master. We'll then use this knowledge to follow a program of evaluating inferences from samples to the population being sampled. So first, a diagram. A diagram for statistical situations will first identify the population that we're interested in learning something about, and second, a model for it. Then, relevant to the population is a sample of it, and a model of that sample as well. So you generate the model, the sample model from the model. We're going to be looking for fit between the left side of our diagram, the items on the left side, and the items on the right side. And again, of course, you generate the sample of the population from the population itself. What are these models? What do they look like? There are only three. The first kind is a proportion model. The second kind is a distribution model. And the third kind is a correlation model. The correlation model will be the one that we use most of the time, but we need to understand the other two models in order to characterize and understand what a proportion model, what a correlation model involves. And you can look on page 172, at least 172 of the edition I'm using in the Geary book, where he tells you that these are all the possibilities that there are. So a proportion model is a model that has one variable with two values. Think of flipping a coin. It can come up one of two possible values. So there's one variable, and the two values are heads and tails. So if you collect a sample from that, flip the coin 100 times, you will be able to generate a proportion model. A distribution model, the only difference is you still have one variable, but you have more than two values. So think of rolling a fair die. Dies have typically 6 sides. If it's fair, each of them has the same probability of coming up, but there are more than two values. So the coin has two values, the die has more than two values. A correlation model arises when we up the number of variables from 1 to 2, and we have two values for each. And what we're asking about is whether our sample confirms or disconfirms a correlation between those two variables. So it's very simple to understand the conceptual background for statistical models. You get three kinds of models. The one we're most going to use is the correlation model. And there you have two variables, and you're interested in knowing the relationship between the two. So what terminology do we need for understanding these models? As I said, the fundamental notions involve proportions, variables, and distributions. Correlations, positive and negative, arise in terms of relations between variables. You've got two variables. Correlations can be positive or negative between those variables. And we also need some way of understanding the strength of the correlation between the two. In the Geary book, Geary suggests relying on the simple measure. We characterized this in the earlier part of the course when I talked about degrees of confirmation. So the simple measure is you just subtract the percentage of things in the sample that fall under one variable with things in the sample that fall under the other. So suppose you have 70%, you're thinking about, let's do a political one. You're thinking about people above and below the poverty line, whatever that is, and whether they vote Democrat or Republican. So suppose in your sample, you've got 20% below the poverty line and 80% above the poverty line. and then suppose Democrat or Republican. Let's say if you're below the poverty line, you've got 80% Democrat and 20% Republican. The difference method says you measure the strength of the correlation just by subtracting those two numbers. So here the strength of the correlation would be 0.6. The nice part about the simple measure is it's easy to apply, it's easy to remember, it's statistically unsophisticated. So if you want to see what statisticians do, there's a footnote that points you to the appendix where you can see how statistical measures differ from this simple measure. For the statistical measure, you're looking for an R-squared value, and you can look that up. We're not going to spend much time worrying about that particular feature in the textbook. It's just if you're interested to see what statisticians gravitate toward, look at that. Besides the strength of the correlation, no matter how measured, we need some understanding of the notion of the margin of error here. So remember, the strength of the correlation is something that's generated from the sample itself. And the sample is not the population. So what we need to do is be able to characterize something about the difference between what we found in the sample and what we should expect in the population at large. For that, to characterize margin of error, we need to be able to characterize the statistical significance of what we found in the sample and develop some understanding of standard deviations. To do that, we need to delve into probability theory a little bit. I'm not going to talk that much in these slides about the mathematical notion of probability. I'll do that in the next lecture. But probabilities are proportions. That's the first thing to note about them, which form the basis for understanding both distributions and correlations. The goal is to get sampling distributions where we compare the various possible values of a random variable with the probability of each, and then the graph of this relationship can be used to explain the notion of standard deviations. We then use the notion of standard deviations to calculate the fit between the models and the reality which they're modeling, measuring the strength of our evidence in the process. So here's some pictures from the Geary book. Notice what you're graphing is the number of trials that you've got. So for example, suppose I forget what the R and Y are here, what the X and Y and the probability of Y is, but we can use a simple example of heads and tails because the probability of getting any particular toss to come up ahead is 0.5. Notice if you toss a coin 4 times, the possible values that you get. You can have no heads or all heads. You can have 1 head and 3 tails, or 3 heads and 1 tail, or you can get 2 of each. Now notice our diagram here is abstracting somewhat from the actual sequence. So think about all the possible sequences you could get. You can get head, 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 head. That's one possible sequence. And then you can get head, 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 tail. Then you can get head, head, tail, head. I'm doing it for purposes of illustrating what happens when you get 3 and 1. Head, tail, head, head, tail, head, head, head. So notice there are 4 actual sequences of tosses, all of which get you 3 heads and 1 tail. So whatever value of the total number of possible sequences there are for all heads, we should get a probability that's 4 times as much for 3 heads and 1 tail, because there are 4 different actual sequences. And notice that's exactly what we get in our diagram. If this is 4 heads, and this is a 3-to-1 ratio of heads to tails, there are 4 times as many of the one as the other. Now notice there's a rounding error here. This is really 0.0625, because divide 0.25 by 4 and that's the value you get. Geary in the textbook just left off the last digit, so it looks like there's some variance between what I'm saying and what the diagram shows. But this is a rounded thing. If you had rounded as I was taught to round, you'd put 0.063 because you round up at the 0.5 level and above. In any case, that's what's going on. So the same thing will happen on the other end. 4 tails has a certain probability. 3 tails and 1 head has 4 times that probability. And then when you sum each of these, you'll find out how much is left. So there's one way to get 4 tails, one way to get 4 heads, 4 ways here, 4 ways here, and ask yourself how many possible sequences of tosses are there when you are tossing a fair coin 4 times. Well, the answer to that is you get 2 possible values for each one. So the number of possible results of trials is 16. And we've got 5 over here, 5 over here, so that leaves 6 here. And we know what the probability of any given trial is, which is 1 over 16, any particular sequence that results from a trial. And so 3/16 is 0.375. Now, the important thing to note here is the relationship between the number of 16, which is the total possible sequences of results on 4 tosses of heads, with what this diagram is showing. So this diagram is collecting some precise sequences of tosses together to generate a number. So this number here was, as I was describing in the example, 3 heads and 1 tail. This number here is 3 tails and 1 head. This is 2 of each. And there are 6 actual sequences that fall under this description. So the description of each of these items collects together some specific singular results of doing the tossing of the coin 4 times. That's important to realize because distributions collect together different possible sequences. And that's why you get higher probabilities here than you get at the ends, because there's only one way for each of these to occur, but there are 4 ways for that to happen, and there are 6 ways for that to happen. I am belaboring this point with this diagram, because once you understand it, you can see why this distribution pattern is going to change as the number of trials increases. It's going to change because the pole numbers are still going to be low, because as you go up in the number of trials that you run, there's still only one way to get that extreme value. So if you toss the coin 5 times, there's still only one way to get 5 heads and only one way to get 5 tails. And I'll leave it to you to calculate how many ways there are to get, if you're doing 5 trials, 4 heads and 1 tail, or 1 head and 4 tails. And how many ways there are to get 3 heads and 2 tails, 2 heads and 3 tails. But you can see what's happening as we do this. You get a distribution pattern depending on the grouping that you're having and the number of possible ways there are to get a particular sequence of heads and tails to fall into each of these groups. So what's being represented is a collection. This is a collection of sequences. So is this, it's just that there's only one possible way to do that. So if the coin is a fair coin, the most likely outcome is 3 of one and 2 of another. And it turns out that's pretty likely. You'd sum those 2 values to do the disjunction. But it's not certain because there are outliers. So you get a distribution pattern and it has a tail. The tail is the extreme regions. And notice there are ways that you could figure out how much of the tail do we want to discount because we view it as so unlikely. So suppose you're doing proportion of people in, let's say, Clayton. Let's sample people in Clayton. You can vote Republican or Democrat, and you just start doing your sample, and you sample on a number of days, or maybe you do it across years. Maybe you're interested in seeing how voting patterns change over time or voting attitudes change. So maybe you're sampling in each of the years of Obama's presidency and trying to figure out what percentage of the population is going to be voting Republican or not. So you can do the number of trials and you get Republican or Democrat, depending on how you're doing that. For a 4-year presidency, I guess you could do 1 each year and you'd have 4 trials. Maybe you do it the first 5 years of a presidency. But notice what happens as the number of trials increases. So here's a diagram, go back to our heads and tails tossing, where the probability is 1/2. As you might expect, the most likely result is that on 10 trials you get half of them coming up heads and half of them tails. But notice where the value of this is. It's now at the 0.25 level. Notice then the difference between these 2 cases. When you draw a chart for what happens with 4 trials versus 5 trials, the highest value goes down as the number of trials increase. And that's the pattern that we want to attend to for understanding distributions. From 4 to 5 trials, the most likely outcome drops from 0.375 to 0.312. This pattern continues. When you go to 10 trials, the most likely outcome drops to 0.25. When you go to 25 trials, the most likely outcome drops below the 0.2 level. And when you go to 50 trials, the most likely outcome is even lower. Similarly, for 100 trials, 150 trials, 500 trials. Now notice what's happening as well here. As we go to larger numbers, suppose you're interested in grouping together a certain percentage of the total possible outcomes. Suppose you want to group together, say, 95% of the total possible outcomes. We'll do that with 4 trials, and you can't leave out the extremes. because if you sum together the extremes and include only these, you're going to get 0.875 of the total possible outcomes. So if you want to draw a circle around all of the values that sum to at least 95%, you're going to have to do the whole diagram here. Notice you're getting closer here, but you're still going to have to do the same thing here. If you want 95% of the cases to fall within your circle, you can't exclude the two extreme values because they sum to more than 0.05. When we get to 10, however, and you want to sum everything that gets you at least 95% of the cases, I can't tell for sure what this value is here. If it were, I don't know, suppose it's 0.025. If that were the case, then we could exclude these two extremes and do this. Draw our circle around the 0.2 to 0.8 region. We'd say that's the region that gives us 95% of the total possible cases. When we go up to 25 trials, according to this diagram, we'd be, I think I'm circling wrong. This little bar at the bottom is Geary's mark for my idea of a circle. So now the circle would run from 0.3 to 0.7. So the relationship here to notice is as the peak goes down, the circle we draw narrows. It shrinks from left to right. So the top thing goes down and this bar across the bottom shrinks. So at 50 trials, we're now barely outside of the 0.4 to 0.6 bar range. That's going to be crucial for understanding the notion of statistical significance and margins of error. And by the time we get up to 500 trials, the range here that encompasses 95% of the total possible values for tossing the coin 500 times gets very small indeed. The point then is this fact about distributions, the peak gets lower, but the range of cases that encompasses 95% of the total possible outcomes narrows. That's why when you're doing sampling, large samples are better than small ones, because the range narrows on the chance that you're having an outlier result from the sample that you gleaned, that you used. So that helps us move toward the notion of a standard deviation. A standard deviation is a measure of how much confidence, it helps us understand how much confidence we can have in the idea that our sample lines up with the population itself. So what we need is a measure of, I guess we don't need two occurrences of the word of. What we need is a measure of how spread out the data are. Since different spreads of the data can yield the same average mean. So I'm going to give you the abstract account of how to do this, and then we're going to apply it to a specific case. The example will help you understand what we're after. So one idea is that the measure we want is this one. This is the one that we define standard deviation in terms of the square root of the variance. So what does that mean? The variance is the average of the squared differences from the mean for each data point. So first, figure out what the mean is. Then calculate the variance. square each, take the average, and then take the square root of the average. That's the actual sequence of steps we go through. So here's an example, and let's apply that. So suppose you have 5 horses. If you like horses as much as I do, you might actually be interested in what your horses are. So let's say you have a Shetland, a Percheron. Shetlands are small, Percherons are big, thoroughbreds are fast, cutting horses are the best athletes you've ever seen among horses, and halter horses are pretty, but they can't do much. Cutting horses are way more athletic. In any case, let's do this in metric measures rather than hands, as we do in America at least, because hands are a rather coarse instrument. A hand is 4 inches. So if a horse is 16 hands, and the next one is 15 hands, there's 4 inches that separate them, and that's not a very fine-grained measure. So let's measure them in millimeters. So our Shetland is 300 millimeters, Percheron 500, thoroughbred is 450, cutting horse is 400, and halter horse 425. So suppose those are the actual heights of our horses. So first calculate the mean. What's the average of those 5 numbers? The answer is 415 millimeters. Second step is, for each horse, calculate how far their height is from the mean. So for the Percheron, you take 415 from 300. And the differences we end up with are then, the Percheron is 115 below the mean. The Shetland is 115 below the mean. Percheron's 85 above it. The thoroughbred is 35 above it. Our cutting horse is 15 below it, and our halter horse is 10 meters above it. Okay, so that's the differences. We've now got the mean. We've got differences from the mean, and then we have to square these differences. The squares are, you can pull out your calculator to check this. Every square has to be a positive number because 2 negatives times each other gives you a positive. So we get these 5 values for the squares, and then we take the mean of these. And the mean of those 5 numbers is 4,400. And then we take the square root of that. And the square root of 4,400 is approximately 66. That is the standard deviation. It's a measure of how far from the mean our values lie. And now we can do that to draw a boundary around the region that encompasses 1 standard deviation, which would be 66, 2, which would be, 132, 3 would be, 198. You can take that from the mean. So if you take 66 to the left and the right of 415, you get 1 standard deviation. If you take 132, you get a different number. And if you take 198, you get a measure of the spread of the data within 3 standard deviations. That's the general idea of a standard deviation. So here's a picture. You take your mean, and then you go 1 standard deviation either way, gets you a certain spread of the data. 2 gets you a wider spread of the data. And 3 gets you an even wider. So 1 standard deviation covers 2/3 of the possible results on your chart. 2 standard deviations gets you 95%, and 3 gets you approximately 99% of those cases. Let's look at this one more time. So suppose you do a sampling and you get a particular result, and you know what the standard deviation is with respect to the sample that you've got, because standard deviation here is determined by size of the sample. So you know what the standard deviation is. Now you should be able to see that what we're going to do is be able to go from the idea of standard deviations to confidence levels. How confident do you want to be that the population matches your sample? 67% is a pretty low threshold. Most people are not happy with that level of margins of error. So the standard number, which in some sense is stipulative and arbitrary, but it derives from the initial work in statistics by Fisher in 1925, when he said 95% is pretty good. We'll only be wrong 1 out of 20 times. Something like that is supposed to be a high enough level to be confident in. Okay, so that's a little bit building up our terminology to the place where we understand what a statistical model is going to look like and what the notion of standard deviation amounts to. How does this help us evaluate statistical hypotheses? Well, a statistical hypothesis, we first have to know what the relative frequency is in the sample that we've got. And that's what our charts have been giving us a diagram of with respect to all the possibilities available. But if you do a sample, you get one of those particular results. Then we have to have some notion of how we're going to estimate what the probability in the population is, and we have to have some understanding of the notion of probability itself. Notice that the links here depend on the assumption of random sampling to generate the sample data from the population. That's going to be a corrupting influence because in most of the samples that we look at that get reported in newspapers and the like, the sample isn't random. Think of political surveys. There's not a random sample ever used when you're trying to predict who's going to vote for whom in a presidential election, for example. You can do a random sample. Suppose we're interested in the percentage of people in this class and who they're going to vote for in the next presidential election, a Democrat or a Republican. Let's assume there isn't any third alternative, so there's only 2 on the ballot. Well, we could do a random sample. There's only 35 people in the class. We could figure out some device, put everybody's name in a hat, shake it up very carefully, and then draw a sample of, say, 10 people. We could do that. The problem is you can't do that on large-scale populations. So the samples aren't generally going to be random. And what we have to say in the first instance here about statistical hypotheses is built on the assumption of random sampling. Next, we're going to talk about confidence levels and margins of error. And we will link this notion of margin of error with the quality of the evidence we get for a correlation. And we're going to try to get some measure of the strength of the correlation that we've got as well. When we do survey samples, we have to face some common problems. So here's one thing that I noticed. So my first job was at Texas A&M. Well, it's actually my second job after getting done with graduate school. It was at Texas A&M, big state university. And there was a local issue on the ballot. I can't remember what it was, but there was people in Bryan and College Station voted, and they were going to have a common policy for the 2 cities. The television station wanted to predict how the election was going to go, which was on a Tuesday. So they went to the mall on a Monday afternoon at 2 o'clock and just stopped people who were walking around the mall and asked them how they were going to vote on the issue. And then they reported it on the evening news. They said the ballot was going to pass. It looked like there was about 80% support for the initiative. So they had a sample. 80% in the sample were in favor. How confident does that make you that the ballot will pass, or that it will pass with roughly 4 out of 5 people supporting it? You will be, I'm certain all of you will think, oh, that's a terrible way to proceed. And you'd be exactly right. There's absolutely nothing random about that sample at all. The history of non-random sampling. First, how many people on a Monday afternoon are at the mall? I think they don't have normal jobs. People with normal jobs are at work. How many people go to the mall? Is there any correlation between people who go to the mall and people who vote certain ways? Maybe, I don't know. But in any case, this is clearly not a random sample. My favorite example of non-random sampling in history is the Reader's Digest poll on one of FDR's elections. I think it was the 36th election. And I can't remember who the opponent was. You can look it up. But Reader's Digest took a poll and said, and predicted that FDR was going to lose by a landslide. I think the opponent's name starts with an L. So they said L was going to win in a landslide. And it turns out it wasn't even close. FDR, whoops, not FDR, not FRD. The Reader's Digest predicted FDR was going to lose in a landslide, but he won fairly easily. What went wrong? Well, here's the sampling technique that the Reader's Digest used. They got phone books from all across the country, used that. I think they did a double random sampling. So they had phone books from around the country, but let's suppose you just collected all of the names in all of the phone books from around the country and then did a random sample from that list of names. It's a big, god-awful list of names, but suppose that's what you did. So now you got a random sample of all the people listed in phone books. Is that random? No, it clearly isn't. For a sample to be random, every member of the population has to have an equal chance of showing up in your sample. There are some people that aren't in phone books. Maybe their number is unlisted. But remember, this was 1936, so think about who has phones and who doesn't have phones in 1936. Rich people have phones. Rich people also tend to vote for Republicans in the 1930s. It was all the rest of the country that was in a depression that favored FDR. So that was the last survey that Reader's Digest ever did. It was so embarrassing. They did it so badly and got it so wrong that they just swore off political polling forever. Other issues are reliability of the information that you get, multiple variables in a single survey, and then publishing only the most surprising. We'll actually look at the chocolate study when we come to p-hacking. This is a particular kind of p-hacking. This is a different sort of issue, the unreliability of the information. So let me finish the thought on the chocolate survey. So suppose you are a manufacturer of chocolate and you want to know, what can we use to advertise the benefits of eating my product? And so you hire a company to do some statistical studies on correlating chocolate consumption with various sorts of things. So you test it, trying to correlate it, or you're looking for negative correlations with, say, heart disease, diabetes, weight gain, acne in teenagers, hair loss in aging men. You correlate it with everything. You do these studies with everything you can possibly find. And then you cull the things that don't make your product look very good, and you use the stuff that does make it look good. So in particular, you had a study with many, many variables. In the chocolate case that we're going to look at, there were actually 30 variables in the study. And one of the results of the study was a correlation between eating chocolate every day and losing weight. This is a particular version of p-hacking to do this. And we will take a look at this later because it's a fascinating topic. And it's also one that you need critical skills for detecting because people cheat you a lot by using p-hacking. I told my son this. It's interesting to notice what people remember of what you say. And actually what I would like is 20 years down the road, if you remember anything from this class, it'd be interesting to know, what do you recall from the class? But in any case, I did this with my son. My son is in his mid-30s. And I said, tell me some stuff you remember about being grown up. And his one thing that he remembers, the most distinctive thing, is that I used to tell him something related to this. What I told him was, Jared, people my age are singularly gifted at getting money out of your pocket and into our pockets. Older adults have developed a skill for getting money to flow from younger people's pockets to their pockets. This p-hacking method is one of those skills that people develop. So in any case, you got to watch out for it. Now, what about unreliability of information? Well, suppose you're interested in correlating certain medical conditions. So I know people have worried about birth control pills and breast cancer, birth control pills and all sorts of other things. So suppose you're going to gather data on a population of women where you're looking at whether they have breast cancer and whether they were taking birth control pills. So you're going to gather your data from these women. Do you have breast cancer or don't you? And then you'll set up some parameters. Have you been taking birth control pills for, let's say, at least any time in the last 5 years? And so now you get a sample that gives you a percentage of your population that has breast cancer and has taken birth control pills in the last 5 years. There's a really serious danger of unreliability here because you're counting on accurate reporting. And it turns out a woman who has breast cancer will almost always be looking for an answer to the why question. And if you do a study and talk about taking birth control pills, the idea pops up in the mind of the person who has breast cancer. Oh crap, it's probably the birth control pills. And then they over-report. This is a well-documented fact. When you compare the medical records of people in surveys of this sort with their actual answers on whether they've taken birth control pills in the last 5 years, it turns out the numbers don't match up. People over-report whether or not they've taken birth control pills in the last 5 years because they're just going on memory. And if the memories are unreliable, which memories tend to have serious reliability issues, that's another problem with the sampling that you're engaging in. So multiple variables in a single study, non-random issues, the reliability of the information that you're getting, those are all problems. And I'll let you look at the HBSC survey that Geary talks about in the book, because this is a very, very carefully done study. And it's interesting to notice the extent to which these problems are attempted to be addressed in the collection of the survey. So the first thing it tries to do is to compensate for non-random sampling. And you can take a look at the measures that they went to avoid the problem of non-random sampling. When we do political surveys, for example, the sample isn't random. So what survey operatives are doing is they look at known correlations with voting patterns. So maybe race is one, maybe income level is another, maybe geographic region is another. Maybe all of these things correlate in one way or another with how people vote. And so you want to know what the percentages are in the population at each of these levels, and then you build your sample so that it matches. so that your sample has the same percentage of each race in it that you know the population at large has. So you try to control for random sampling by taking into account all the correlations that you know about. And the HBSC survey did exactly that as well. It went to great lengths to compensate for the fact that you couldn't do random sampling. Now notice the difference as well between the population of interest. This is a crucial thing to pay attention to. And the population actually sampled. So the population of interest is basically teenagers. Well, teenagers before they graduate from high school. So basically, let's say 13 to 18, but they didn't actually sample 13 to 18-year-olds. They sampled, what was it? Was it 12 to 15? Anyway, look it up. The population actually sampled was not the same as the population of interest. That should raise a question mark in your mind. Is it possible that the population sampled and the population of interest differ? Of course it's possible, but do you have any reasonable expectation that there might be differences? To the extent that you have reasonable expectations that there might be differences, and that they might be important ones, you have a reason to be suspicious about the results of the survey. And notice the difference in the correlations that we're interested in and the correlations that we get. So we're trying to correlate fighting and bullying with what country you're in. And maybe, for example, you expect Americans to be more pugnacious than Brits. So look at the correlations and see. Maybe you get surprising results. So take a look at that survey. It's a really intriguing one containing lots of information and lots of ways in which you can generate correlational data. So what are the steps of the Geary program that we use when we apply it to this study? First thing to do is identify the population. And here we must note that the population of interest is not the same as the population sampled. With respect to the sample, we ask, what is the data? Especially identify both the data and the sample size. So the data will give you something about percentages of certain results within the sample, but you have to know something about the sample size in order to apply Geary's program to understanding the study, because we have to note the margin of error for samples of that size on the assumption of randomness. Now, we don't have randomness, so that's going to come into it. But with respect to a given sample size, we need to know what the margin of error is for that sample size. If you can't identify a margin of error because you don't have the sample size, that's a very bad thing. You're then in the dark about what to do. If they don't give you the sample size but do give you a margin of error, that's fine, because it's really what we're after is the margin of error connected to the sample size. The connection between that is what we were talking about earlier with the distribution charts for trials of various sizes. Finally, identify the kind of statistical model relevant to your assessment. So when you do your homework, you have to say, is this a proportion model, a distribution model, or a correlation model? Those are the three options you're given. Finally, with respect to the sample, address the question of the randomness of the sample. Was it random? If not, what steps were taken to try to minimize bias? And then you have to assess, do these really seem to be the best you can do to minimize bias? Will they be good steps? Do you expect bias to be minimized significantly, minimized nearly completely, hardly minimized at all? These are qualitative judgments to make, but they have to be made in applying the Geary program to statistical studies. Finally, identify the statistical hypothesis being evaluated. Does the sample provide strong evidence for it? No evidence? Weak evidence? Whatever you say here, be able to explain your judgment. Finally, can you identify ways to improve on the study question? Should the survey have been worded differently? Is the non-randomness troubling enough to make the data highly suspicious? Those sorts of things. Now, this third element, should the survey have been worded differently? I throw this in because you're probably familiar with push polling. Everybody wants data. And when you publish data saying most people prefer Trump's policies to Biden's or whatever, you have to ask yourself, was a push poll being used in the process here? So one of the standard devices in push polls is that it takes advantage of affirmation bias. Most people, I'm not one of them, but most people tend to be agreeable. Philosophers don't tend to have this trigger switch in them. They tend to be suspicious. But most people tend to be agreeable. If I say, wouldn't you like some chocolate? If you're an agreeable person, you're likely to say yes. Now, it doesn't mean you will, but would you like to X? Would you like this? Would you like that? I can take advantage of the bias to be agreeable in a conversational context, because conversational contexts are governed by a principle of cooperation. If you're going to spend time talking to me, and if I'm going to spend time talking to you, we sort of both implicitly agree to cooperate with each other. And so, don't you want to lose weight? You're inclined to say yes. Now, maybe you're not. Maybe you're worried you weigh too little. I had a grad student once who he kept trying to gain weight because he only weighed 115 pounds and he thought he ought to weigh 140. So he'd say no. But most of us cooperate in conversational contexts. And so questions that are worded so that you answer yes or no are much more highly likely to be responded to in the affirmative. And so you can do push polls because you can ask the same question, get the same information from a person in a way that requires a yes answer as in a way that requires a no answer. So a push poll is constructed so that a yes answer generates a sample result of the sort I'm looking for in my study, and a no answer generates the answer I don't want to see. So you need to say something about the wording of the study as well. That's the program. Its steps involve identify the population, the sample, say something about the randomness issue in the sample, identify the hypothesis being tested, and then address the evaluative question about how you think the wording of the study was done. The HSBC, is that the name of this? HBSC survey went to great lengths on the wording of the survey to avoid that infecting the sample in certain ways. So it's a good example of how to do things well. That completes the background work that we need to do in chapters 5 and 6 in order to evaluate statistical hypotheses. Think of that as an overview. We are also going to work a little bit on probability theory to improve our understanding of p-hacking, of standard deviations, and how the probability judgments that we make and rely on are generated. So in the next video, we'll start talking about probability theory and learn a little bit about the probability calculus and how to become comfortable with using it.